Hey everyone, and thank you for joining the AstrumDrive podcast. As usual, this morning we're joined by Nelson. Nelson is the head of our physics department. So during this podcast, we're going to review what did we do in the last sprint 7, and we're going to take a short overview about our plan for sprint 8. So Nelson, please go ahead and please tell us what did we achieve during sprint 7.
Hi everyone, thank you, Bailo. Uh, sure, let me go briefly of what we did during the last sprint. We did good things, great things regarding our own proposal for the spherical metric warp. We uh, we started basically reviewing how the Einstein's field equations looks when you have this metric and how they behave more or less between them. You have, if you calculate Einstein's equations, you obtain a set of equations, usually are related to each component of Einstein tensor and the energy momentum tensor. So basically what we did was uh, recalculate again uh, almost everything, every calculations we have done since the very beginning, using the codes we have in Mathematica and so on, everything we have developed. And we found a system of equations for the perfect fluid with a spherical warp drive, and also the perfect fluid with cosmological constant included for the warp and spherical symmetry. And it was great. It was great to see because we realized a couple of things. In the case when you have, for instance, Alcubierre's metrics for the warp drive, it's written in Cartesian coordinates. And that's good because it gives you a clear choice of which direction you use for moving the motion of the warp, the motion of the whole bubble, the warp bubble. And in this way, how we are thinking about the warp drive in spherical symmetry uh, is quite different because the radial direction is the same. That you have a symmetry is the same in every direction, and you choose just move in the radial direction. The point of that seems like a, well, what difference you're going to get? Well, there is some difference. For instance, if you use Cartesian coordinates, you find a set of Einstein's equations, a lot of Einstein's equations. But then you realize, as you see the equations, that you can uh, put those equations together. You basically can find that between these equations, you find another constraints or relations that some of the specific components or the specific functions that are included in the metric have to obey. And when you do this, you realize that some things are zero always. There are no way there are not zero, and some things are just have to fulfill some specific relations. This is looks like a small thing at the beginning, but then we realize that you need to use this because these are not uh, constraints that have to be obeyed just if you have some specific situation in the warp drive. These are constraints that are always have to be fulfilled, and they of course then they restrain. I mean they put a limit to whatever you find in the equations. And basically when you use this, it's like if you are removing like a spurious extra uh, the degree of freedoms in the theory that are not going to be really physical. This is a way of interpreting the interpretation of this. So what happens when you go to the spherical symmetry is that you don't get these constraints. And then we realize that what apparently is happening is like uh, we are using the most, let's call it, natural uh, system of coordinates to describe what is going on with the warp. And then you don't obtain these constraints because these constraints are not there. You don't need these constraints. You don't have extra degrees of freedoms that you're going to remove. And also you obtain less equations from Einstein's equations. In this case, we have five Einstein's equations that are independent, and it's very good, very good. Nevertheless, these are complicated. We have to work on them, but it was very interesting to find out that we are obtaining this, and this is a signal of that doing we're going into the right path. It's a good track that we're walking. That's one thing what we did during the spring, which is of course now related to the article that we start putting together during this spring that is finishing. Another thing that we did is we make a long reviewing of what's going on with Bobrik's proposal for constructing a warp drive. It's quite interesting. The Bobrik proposes a classification for warps that comes from the velocity of the warp with respect to some observer and a relation between this observer and the observers that are in co-motion with the warp bubble. And there is a specific relations that you can set between these two, and this relation and the velocity gives you like a family of solutions, and you can classify, or they did, in four classes. And they're very interesting. I mean, the four classes include two type of motions that are subluminal, which means that you're moving under the speed of light, still very fast, but not at the speed of light, and two more that are superluminal, which means that you're moving faster than the speed of light. Uh, and this very nice construction they put there, because on the one hand you have these four classes, so you can determine whether your metric is, and you can put it together with another metrics. For instance, they did it with Alcubierre's metric, and it comes into classes, class 3 and class 1. But the most interesting thing for me, at least, which we found mm, good for our research, is that to construct these metrics, thinking in what they have in mind, which is the relation between these observers and the fact that you can move faster or slower than the speed of light. And it's quite interesting because they made like a more or less general proposal for how to construct the metrics. They did it in Cartesian coordinates to start with, uh, and how it looks is quite natural to construct the warp metrics. So the good thing is that we can include our metric into this, and our metric is a bit of a construction, but not in Cartesian coordinates, of what they're doing in Cartesian coordinates, which is almost like a construction where you make a deformation space-time in a given coordinate, a specific coordinate. It's quite interesting this way, and we obtain these results. And the point of that is like, with that in mind, we were able to put in which classes we have our metric, which by the way is they are in the same classes of Alcubierre, and also we got to study some problems that they put into onto the table that are regarding the sphericity of the warp bubble, and how this can affect the if you are moving faster than light. And that's one other thing that we figured out, since we are working with spherical bubbles, at least as a first approach, we're going to get the same problems. And the problems are, we can think, I've been thinking how to put this together in a simple way. Is if you're moving very fast, you know, a simple way to looking at this is like your sphere is going to deform, because you have a mapping between a bubble. We look, which is the observer that is important, because it's the observer that we can say the lab observer, that is seeing how you're moving very fast from one point A to one point B. Well, the point is that this observer will look to this sphere deforming. It's no longer a sphere. And the fact that it's no longer a sphere gives you a lot of problems in the description of how the motion is occurring, because it's not just a matter of, oh, but this is a bubble that is moving. No, it's a matter of the space time that you are constructing to keep this construction of warping have some properties that you have to fulfill. And one of these is like you need that the construction basically gives you some vectors that are orthogonal to this surface that are always pointing in a specific way into the space-time. Basically, what you say is you need these vectors to be time-like all the time. And once you start deforming the bubble, you don't get to these vectors to be time-like anymore. They start to have space-like components, and that's a problem. That's really a problem, and that's in fact related to the with the symmetry of of the system, how it's conceived now. Of course, we're thinking already how to solve this, but what we achieved during the sprint is like figuring out what's the problem, what was the problem, how to calculate the problem, which is calculating the Killing equations and solving Killing equations, and see how these equations tells you about a general way to tells you how the symmetry of the problem is. And we implemented all this in Mathematica. It was very nice. We have some problems and now we're thinking about a solution, which is, if I can tell you already, is well, let's start with some configuration that as you deform, maybe is going to get the right warp symmetry that we want. So it's like playing backwards or like inverse engineering the warp in a sense. We're not sure about this yet, but this is something that we will study later. And well, I think that that's the most important thing about what we did during the sprint was also find out we have a simple way for including spinning of the bubble ward drive, which is very nice, and also a very nice thing that we're still studying because it's related to what we think is our next step in the work. Is like what when you have observers that are which are time component between them inside from inside or from in commotion with the word drive, and another one that is not in commotion with the word drive. These two observers, the time component is mapped in a certain way. It's not just a simple trivial way, which is more or less what everybody does do. Sorry, but a more complicated way. And depending of this mapping, apparently you can obtain a more general type of word drive, which can be related to the fact that you use a different lapse function. And the lapse function is, in a simple way, is a function that appears in the metric when you construct the space-time at the very beginning. And in most warps, you just set this to one constant. And although that's good, it's not a problem. This comes from it's been proved in a very nice article that we review, and that it's not as general as people thought. I mean, people thought in general. Let me tell you very briefly this, that it's good enough to put one there because you have in cosmological models you need to fulfill some very specific characteristics. I mean, you need isotropy, you need this type of symmetries of the matter that are going to be in the cosmological models. And the point is that if that's so, you obtain certain equation of states that are compatible with this setting this lapse function to one. And if you and basically what this tell you is like you can always make some transformation that can gives you a lapse function that is equal to one. This is called like some sort of gauge transformation. What this has been found recently, very recently, 1 year, 2019, 2020, is like this is not as general as they thought. There are some constraints there, and we're looking into those constraints to to work this out on warp scenarios, because on warp scenarios we were not restricted to this type of symmetries of the energy momentum tensor isotropy, for instance, that cosmological models have. They are very similar in a lot of senses, but they are also quite different in many others. And that's basically the physical part that we put together during the sprint.
Excellent. Thank you very much, Nelson. So I want to bring something which we discussed, which I think is going to be quite interesting. So we're talking about spherical warp drives, but we find out that when we have the superluminal speed, this sphericity is not going to be kept. Do you mind to talk a little bit about that?
Sorry, I didn't catch the last thing you said.
Yeah,
Can you repeat it?
yeah, so, sure. So we talk a lot about spherical warp bubbles, and we
Yeah.
found something in our calculations that if we travel with superluminal speeds using spherical warp bubbles, the sphericity is not going to be kept, it's going to change. Do you mind to talk a little bit about that?
Yeah, yeah. But well, as I mentioned before, yeah, it's you can think about of that in the most simple way. Is like when you think about length construction in special relativity. This is a way of thinking about it. There are some works that prove that the things that move faster than light, than the speed of light, these are tachyons basically, and there are a lot of works related to tachyon physics. Uh, this tachyon behavior from special relativity. I'm talking about special relativity now. So we are in a sense in a specific observer in a local neighborhood of what is going on in the physics. But this tachyon situation tells you that if you have something that is moving close to the speed of light, but above the speed of light, is still going to deform in the more or less in the same way that you have length contraction when you are starting to move very fast, very close to the speed of light. I mean, you are 60, 80% of the speed of light, and you will see the formation of the length, a length contraction, and it's pretty much you can see like the same effect. So basically, you have a deformation of the sphere, and that's already going to change the metric, because changing the sphere is equivalent to changing the metric. So whatever you were using before to describe the motion is no longer there. So the model crashes. So you need to find out, which is our thinking, to find out how to write down a transition, which means that you have something that's going to be dynamical, and that's a lot. It's complicated, but it's complicated doesn't mean that it's impossible. It's just we have to work on that, and that's basically the idea. I think this is the best way to put it together. The idea of the why is there is a problem if you are there at those faster than speed of light velocities.
Excellent. Thank you very much, Nelson. It was really interesting. So I wanted to bring it during this discussion. And do you have anything else to say about the Sprint 7, or we can do a short overview what we're trying to achieve in Sprint 8?
Yeah, well, we have during next sprints we have a lot of good, nice results. We think we put together to start writing an article to send for publication as soon as we can, at least for start the reviewing process with some referees. And I think that that's basically what we're going to do during the next sprint, which is maybe not too interesting in terms of podcast, but it's going to be quite interesting when you guys will be able to read the article and what are the results of all this work we have to be doing. But anyway, uh, we're still going to work on the labs function that I told you before. where we think that is if we don't use the labs function set to 1, we are going to have most general uh, Einstein's equations, which means that basically saying if you think of Einstein tensor as a matrix, uh, some elements of this matrix are going to be 0, depending of the symmetry of the coordinate system you use and so on. If these matrix elements are 0 in one side of the equation, then the other side of the equation, remember this is equal to some other matrix that is the energy momentum tensor. So if from one side is 0, then the same elements in the other side, the right hand side, has to be 0 too. I mean, this is a coherence between the equation. There's an equal sign in the middle. And then the point is that, so in the way what I'm trying to say in the most simple way I can think of is that if we put the lapse function more general, we expect to obtain different from 0 components that were 0 before in the Einstein's equations, which means that you can be more creative and have more freedom to put in the right hand side in the energy momentum tensor more things, more quantities, more elements, matrix elements or components. Each of these components have a very specific physical meaning, depending of where they are and how they relate to the proper component in the left hand, right side, the left hand of the where Einstein components are. Basically, this is the basic idea of what we're trying to achieve the next sprint, impartially during the next sprint, and then during the next other sprints. We think we can add in this way some dissipation in the system, for instance, and maybe some relation between these dissipations and other components, which is going to be also very, very interesting and can have an impact of everything else. But this is something that, well, interesting.
And also, I just want to talk a little bit about the dissipation of the bubble. Can you please explain it a little bit?
Well, dissipation comes in different flavors, if you can think of like that. If you have dissipations, but the basic idea, dissipation means that you are losing something from your system. You define a system. Your system is something specific. In this case, is the word bubble. And one type of dissipations that you can have is like you have thermal dissipation, for example, which means that somehow you have to include into the system something that is going to radiate energy from the system. This, of course, means that if you have this type of dissipation, which is always losing something, it will have an impact of how for example, the radius of the bubble, the conformation of the bubble, this will have an effect on this. So basically, what I'm trying to say is that any dissipation effect we expect to have an impact on the bubble itself, the word bubble itself, uh, and we can use that as a mean of controlling the bubble. What I'm saying is like this is thinking ahead a lot, but it's a very nice idea. You can try to modulate how long the bubble is going to live if you know exactly how the matter that you're using to form the bubble or to keep the bubble formed is going to dissipate. And in that sense, you give the bubble a lifetime, and then you can use to, for instance, accelerate the bubble. I mean, you don't use it to accelerate. You somehow accelerate the bubble, start moving, and depending life, let's call it that way, and the warp motion will stop. So you can say, well, I'm going to move this far. You're going to set up the physical parameters, and the bubble will stop there. So it's a way of controlling the bubble. We think it might work, but not completely sure, but it's a good shot. That's one of the problems we have with the work. I mean, there are some of the problems, the horizon problems with the bubbles, and how they're the causality of the disconnection, causal disconnection between inside and outside, which means that you somehow have to control some of the parameters from outside, and this is one way of controlling.
Excellent, Nelson. Thank you for bringing this point because now when we're trying to understand how to create warp bubbles, what are going to be the governing equations, we want to understand as well how we can um, disappear these bubbles because it's going to be very important to be able to control them in order to be able to project or calculate certain warp movement. So thank you for that. And Nelson, I think this is going to be for this session. Do you have anything else to add into this talk?
No, please, as I always say, interact with us, ask questions, propose things if you wish. We're here. We are all trying to do a nice job, and really want to hear from you guys. And if you can support us, that would be really great. Really, really great. It's important for us.
Thank you very much, Nelson. And thank you very much to everyone who is listening to this podcast. If you guys like it, please share it, subscribe to our channel. You can support us on Patreon. And with that, let me wish to all of you to have a very nice and successful week. Thank you for listening.